Hello, this video serves as a primer for Eaton and Kortum 2002. We'll understand the reason of making certain assumptions about technology in their paper, which are critical to their theoretical framework. In this video, we'll focus on the most important reference on this issue, Kortum 1997. We'll look at several important distributions that commonly used in international trade research, and hopefully we can better understand EK's assumption about technology after this video. Now let's take an overview of Kortum 1997. He develops a general equilibrium search model in this paper covering the fact of exponential growth in the number of researchers but constant in the number of patents. That's the innovation in the research department, such as grants. However, exponential growth in output per worker, that's the innovation of industrial applications. He defined a patent as a research role that advances the technological frontier. And the aggregate rate of patenting depends on two parts. The first part is current research. It's represented by the rate of sampling from the search distribution in this paper. And that's a possibility of a researcher that come up with a new idea. It's new only to him or herself, not to the whole economy. And the second part is the stock of past research. It's represented by the probability that a given draw will advance the technological frontier. So that's the possibility that the idea is new to the whole society. Because as we have more and more researchers, many of them may create the same idea at the same time. But all of those same ideas can only advance the technological frontier once. And Kortum shows in his paper that researchers sample from probability distributions is following a Pareto distribution of potential new techniques. And the research output is summarized by technological frontier. The technological frontier is defined as the most efficient techniques for producing each good in the economy, which follows the Fréchet distribution. Now let's say the assumptions about techniques. Ideas arrive to a researcher as a Poisson process with same parameter mu. A Poisson process describes a series of random events happening over time. The average number of events happening per unit time is constant. In this case, the ideas occurs to a researcher over a given time period is constant, and each event occurs independently. A Poisson distribution calculates the probability of having a specific number of events k occur within a given time period in a Poisson process. It takes the rate lambda, that's the parameter of Poisson distribution, and the desired number of events k as input. And here we can see from this graph, when lambda equals to 1, the blank curve is intensively distributed around 1, and when lambda equals to 5, it's intensively distributed around 5, and the same for 10 and 20. So it means that for a Poisson distribution, it will intensively distributed around the average number of events. That's a parameter in Poisson distribution, lambda. Here, we assume the parameter is mu. And the stock of all past research effort, kt, at time t is defined as the integration of Rs over all past time period, where Rs is the number of researchers, and the number of researchers is smaller than the number of workers. The number of techniques for producing goods J discovered between time t and time S, which is greater than t, has a Poisson distribution with parameter ks minus kt. The efficiency of a technique for producing good J is Q, and the realization of Q is Z, which we will use in the following slides. Basically, they are all the efficiency of techniques. And the technique is puntable, as we mentioned before, if and only if its efficiency surpasses all existing techniques. So the key assumption in this paper is that the search distribution for which the efficiency of a new technique Q is drawn, given a stock of past research K, is in this form. So the FQ here is a stationary search distribution. It tells us the probability of a researcher to come up with an idea. So 1 minus FQ is the probability that a researcher don't come up with an idea. And the logic in this paper is that the more the stock of past research, so the higher the value of K, the more difficult to come up with a new idea, because more and more ideas will be overlapped. So SK multiplied by the 1 minus FQ would be the probability that a researcher can't come up with a new idea. And 1 minus this probability would be the probability that a researcher can produce a new idea. That's the efficiency of a new technique Q is drawn. Then let's see the assumption about market structure and technological frontier. Patent protection expires with when a more efficient technique is discovered. The patent holder maximizes profits by charging the highest price at which competitors don't enter, which is a marginal cost of competitors. Only the most efficient technology will be used in producing good J. And suppose that the patent technique enables good J to be produced at efficiency Z. Given all of these assumptions, it also shows that the distribution J1 of the state-of-art productivity, that's a technological frontier for producing in sector J for a fixed research stock K, is in the following form, and J1 is an extreme value distribution. Let's say the statistical distribution of the largest value drawn from a sample of a given size can take only one of these three possible forms: a Weibull, Fréchet, or Gamble extreme value distribution. For example, draw n numbers from a distribution and record the largest one. Repeating this procedure m times yields m largest numbers, and these m numbers will follow one of the extreme distributions: Weibull, Fréchet, and Gamble. The Weibull distribution usually model minimum, while the Fréchet and Gamble usually model maximum. And the Weibull and Fréchet has lower bound. It means that it only has positive value when the variable is greater than 0, while Gamble doesn't have bound. And specifically, Fréchet distribution has heavy tail, which is closer to partial distribution. Now let's prove it. Due to Poisson arrivals, the emerging of ideas I follows a Poisson distribution with a parameter kt minus ks. So the probability of no idea is discovered between two time period is when the number of events equals to 0, it follows the Poisson distribution with a parameter kt minus ks. So the probability that no technique more efficient than Z is discovered should be in this form. Let's say this is actually the research draw distribution. That this is a distribution of ideas occurs to researchers. So that's a Q in this function. Then the Q, that the no techniques, the Q is greater than Z should be equal to 1 minus the probability that the Q smaller than Z. So if assumption 2.1 holds and the time interval is small enough, the probability that no technique more efficient than Z should be in this form. We basically just combine the research draw distribution, the Poisson distribution, with the previous distribution of the efficiency of a new technique Q. Okay, then the probability of technology at tomorrow, so next time period, is smaller than Z when the current technology is smaller than Z and there is no new technology. So the probability should be the multiplication of these two parts. And if you integrate this differential equation, you will finally get the result in the proposition 2.1. Productivity is defined as the average efficiency of workers, which is represented by the mean of technological frontier. So here, basically, we just calculate the expectation of J1 to get the function of productivity AT. And the relationship between the productivity and research It's therefore sensitive to the functional form of stationary search distribution Fz, which is in the J1 distribution. Let's see three illustrative distributions. The first one is partial distribution, the second one is exponential distribution, and the last one would be uniform distribution. Then simply replacing the function fq in J1 distribution with the three illustrative distributions and compare the function form of the result with the three extreme value distribution, you will find that the partial distribution results in a Fréchet technological frontier, which is J1 distribution, and we could represent the productivity in this function form. The C1 and C0 in different functions are different, but all of these parameters are not relevant to K. And the exponential distribution results in a Gamble J1 distribution, the uniform distribution of FQ resulting in a Weibull J1 distribution. Okay, now we could say that all of these different illustrative distributions can result in some extreme value distribution. So why did he choose Pareto distribution for FQ and the Fréchet distribution for J1? That's because of the distinct growth implication of these three distributions. We choose the functional form of FQ to be Pareto distribution because only this distribution implies sustained exponential growth of productivity. As we can see here that if you, the AT dot means that AT differentiated with respect to time t. So the growth rate of productivity is defined as the ratio between AT dot over AT. And we could say that under the Pareto distribution, the growth rate of productivity is exponential. However, with two other distributions, they are either arithmetic or no growth rate in the long run. That's why Kortum argues that if we want to model the reality, the current reality that there is an exponential growth of productivity, we will have to use the Pareto form for the FQ function, and it will result in the Fréchet distribution of the technological frontier. And these are the main references for this video. Thank you for watching.